In the next exam question, we have a diagram below showing a heavy block with a mass of 100 kilograms sliding down a rough inclined plane. A constant force F is applied on the block parallel to the inclined plane as shown in the diagram below. Even though we have a constant applied force in the upward direction, the block still slides downwards at a constant velocity. The magnitude of the kinetic frictional force between the block and the surface of the incline is 266 Newton. So from the information given, we have said that the block moves at a constant velocity down the incline. This is also a rough surface, which means there is friction, and friction will then be in the upward direction against the direction of motion. The reason why this block is moving downward is because of the parallel gravitational component. We also have the perpendicular component of gravity, as well as our normal force. Make sure to always take note of a constant velocity and write it down somewhere on your diagram where you can see it. 5.1 then says that friction is a non-conservative force. What is meant by the term non-conservative force for a total of 2 marks? Now, in order to explain a non-conservative force, we can make use of the following mnemonic story. Now, imagine that this is a carpet and you are trying to move a little box from point A to point B. Now, the first option that we have is to move it directly towards B. But we are also allowed to be very creative and follow a very silly squiggly path like the orange path. Now, the reason why we would rather move from point A to B in this vertical line is because this would require a lot less work than the orange path. And when a force is path dependent, it means that it is a non-conservative force. If we would take our box, move it from point A to B, and feel the bottom of the box at the end, the box moved on the orange path would have a hotter surface at the end of this route, which means that more energy was lost due to friction. And this tells us that friction is a path-dependent force, meaning that it is a non-conservative force. The longer path would lose a lot more energy than the shorter path. And any force that is path-dependent is a non-conservative force. In 5.2, a learner states that the net work done on the block is greater than 0. 5.2.1 says, is the learner correct? And in 5.2.2, we are asked to explain using physics principles. Now, in order to answer this question, we can have a look at our work-energy theorem, which states that the net work on a system is equal to the change in kinetic energy. Now, remember, change in kinetic energy is a half the final velocity squared minus the initial velocity squared. In this problem, we had a constant velocity, which means that the final velocity and the initial velocity should be the same, which means that the net work on this system should be equal to 0 and not greater than 0. .3 says calculate the magnitude of the force F for a total of 4 marks. Now, in order to solve the applied force, I have to make use of my free body diagram. Remember that we have a constant velocity in the downward direction. Therefore, I would take all the vectors moving down the plane as positive and those in the upward direction as negative. We can now apply Newton's second law of motion in order to solve the applied force. Now, seeing as we have a constant velocity, it means that the acceleration would be equal to 0. And therefore, the net forces would also be equal to 0. The forces working in my direction of motion is my FG parallel, the friction, as well as my applied force. Now remember, for the FG parallel, it is mg sine of theta. Remember that this S in sine stands for the slide, and therefore it is the FG parallel because that is what causes things to slide down an incline. The frictional force was given as 266 Newton. Which gives us an applied force of 148.17 Newton. In the next part, it says that if the block is released from rest without the force F being applied, it moves a total of 3 meters down the inclined plane. In 5.4, they ask, calculate the speed of the block at the bottom of the inclined plane for a total of 6 marks. Now in this part of the problem, we no longer have this applied force up the incline. We were said that the block was released from rest, therefore the initial velocity is equal to 0. And we are asked to calculate the final velocity at the bottom of the plane. Looking at the vectors working on this block, we would still have FG parallel, FG perpendicular, our normal force, as well as friction. Making use of the work energy theorem, we can solve this problem. The forces that does work on the system would be FG parallel as well as friction. The normal force as well as the FG perpendicular are at a 90-degree angle to the displacement, which means that would give you a cos of 90, and the cos of 90 is equal to 0. So the normal force as well as the FG perpendicular does no work on the system. Now this cos of theta is the angle between FG parallel and my displacement. Now both FG parallel as well as displacement is working down the plane. Therefore that would be the cos of 0. The frictional force is moving up the plane, displacement still down the plane. Therefore the angle between these two forces would be 180. Which gives you a final speed of 2.98 meters per second.